Good morning, everyone. Today we're going to talk about limiting reactants. So this will be our key here, and we will get things going with this reminder, right? Again, consider the combustion of propane. Here's propane, C3H8, plus 5 oxygens, yields 3 CO2 molecules and 4 water molecules. Okay? If you had 10 moles of propane to burn, you would need 50 moles of oxygen, according to the ratio in the balanced equation, right? So if I had 10 moles of this, right, because there's 1 to 5 ratio between propane and oxygen, there's a 1 to 5 ratio. So for every mole I have of this, I'm going to need 5 moles of this. So if I have 10 moles of propane, I'm going to need 50 moles of oxygen, or 5 times as much. If you only had 20 moles of oxygen, you couldn't combust all 10 moles of propane. You would run out of oxygen before the reaction was done. The reaction has been limited by the amount of oxygen you have. You don't have enough oxygen to burn all of the propane. In this case, oxygen is called the limiting reactant because it limits how much propane can react. Notice that the limiting reactant isn't always the substance that's present in the fewest number of moles. In this example, propane is the excess reactant because after the reaction there will be some of it left over. It's important to remember that everything in a chemical equation is related by mole ratios. Right? If you only know the mass of the substances, you'll need to convert it to moles first. In the above discussion, it was evident that 20 moles of oxygen was not sufficient to combust 10 moles of propane. How many moles of propane can be combusted with 20 moles of oxygen? Right, well, start off with my 20 moles of oxygen, right? My mole ratio is 5 moles of O2 for every 1 mole of propane, C3H8, right? So that's my equation ratio there. So how many moles, that's what I'm asked for, so that's why I can stop here, right? So I plug it in my calculator here. 20 times 1 divided by 5 equals 4 moles of C3H8. So 4 moles of propane, that's all I can make. How many moles of carbon dioxide will be produced? Okay? I do that the same way. I plug in another, right? Let's see, base the answer to this question on the number of moles of propane that actually get combusted. So they want me to start with this one. So I'll start with 4 moles C3H8. But now, because I'm asked about carbon dioxide, I'll use carbon dioxide from here. So my CO2 and my propane is the ratio that I'll use. So I've got 1 mole of propane, C3H8, for every 3 moles of CO2 that get produced. All right, I want moles of propane, so I can stop there, plug it in my calculator. 4 times 3 divided by 1 should be 12 moles of CO2. All right, verify that if 12.5 moles of propane and 63.2 moles of oxygen were present, then propane is the limiting reactant and oxygen is the excess reactant. Okay, well, I just plug these in. 12.5 moles of C3H8. I plug in my mole ratio from my equation up here, 1 of those, and what are we looking for? Right? I want to know if oxygen is the limiting reactant or propane. Okay, so I can use that and this. I'm just going to convert this. How many moles of oxygen do I need to convert this? So I've got 5 moles of O2 for every 1 mole of C3H8. Okay, I'm using this one because it doesn't matter here. I'm not asked about the carbon dioxide or the water. I'm just asked about this. I know how much of this I have. What I'm doing is calculating how much oxygen I need to react with the amount of propane I have, and then I can compare with how much I have. Okay, so let's plug this in our calculator. 12.5 times 5 divided by 1, 62.5 moles of oxygen is needed. Right? 62.5 moles of O2 is less than 63.2 moles of oxygen on hand. Right? And so I only need this amount to react with my propane, so my propane runs out before I use all of the oxygen. So my propane is the limiting reactant. Okay? Let's take a look at the next page. All right? We have a new equation, but you'll see that these problems all kind of work out the same way, right? Consider the following chemical reaction. 3 magnesium chlorides reacts with 2 sodium phosphates to produce 6 sodium chlorides and magnesium phosphate. Assume I have 0.75 moles of magnesium chloride and 0.65 moles of sodium phosphate in a reaction vessel. Verify that this is the excess and this is the limiting reactant. Right? So if I want to do that, I'm going to start with my 0.75 moles of MgCl2. I'm going to multiply it by my mole ratio, and I'm going to compare it to the other one. So I'm going to use this one. So I have this. I'm going to use this because that's what I'm comparing it to. All right, so my ratio is 2 moles Na3PO4 for every 3 moles MgCl2. Okay, so let's plug this in. 0.75 times 2 divided by 3 equals 0.5 moles Na3PO4. This is how much sodium phosphate I need to react with my magnesium chloride. I'm told I have 0.65 moles. Okay, how many moles of the excess reactant are left over? Well, I have 0.65 moles Na3PO4 on hand. I'm going to use up 0.5 moles of Na3PO4. So if I subtract those, I'm going to get, write it over here, 0.15 moles Na3PO4 left over. Alright, just to confirm that, 0.65 minus 0.5, yeah, 0.15. Right? How many moles of NaCl will be produced in this reaction? Okay, I must base this answer on how many moles of the limiting reactant that's react. Okay, so if my limiting reactant is my magnesium chloride, right, I have to start there. So 0.75 moles of MgCl2 times, in this case, I'm interested in moles of NaCl, so I have to use that one. 6 moles, that's where I'm trying to get to, NaCl for every 3 moles of MgCl2 I use up. Right? So let's plug that in. 0.75 times 6 divided by 3, 1.5 moles of NaCl is produced. Okay, now consider the double replacement reaction between calcium sulfate and sodium iodide. If 34.7 grams of calcium sulfate and 58.3 grams of sodium iodide are placed in a reaction vessel, how many grams of each product will be produced? Okay, do this problem in the steps outlined below. So they've given us all the steps. All right, so we need a balanced equation first. Right? So I'm going to have calcium sulfate, CaSO4, is going to react with Na I'm going to have a reaction that occurs. This is an ionic compound, this is an ionic compound, so it's going to be a double replacement reaction. The calcium and the iodine will get together. Calcium is a +2 charge ion, and iodine is a -1 charge ion. So I'm going to have CaI2. And to that, I'm going to get sodium and sulfate. Sodium is a +1 ion, but sulfate is a -2 ion. So I'm going to have 2 sulfates, or 2 sodiums on that sulfate. Right? And so now I have my compounds written. Now I can balance the equation. So I have 1 calcium here, 1 calcium here. That looks good. I have 1 sodium here, but 2 sodiums here. So I'm going to put a 2 there. That gets me 2 iodines, which is good because I need 2 iodines there. And I have a sulfate, and I have 1 sulfate. So that balances my equation. All right. First, find the limiting reactant. First, convert 34.7 grams and 58.3 grams from grams to moles using the molar mass. All right, so 34.7 grams of calcium sulfate. I need to add that up for my molar mass. So calcium is here, 40.08, plus a sulfur from here, 32.07, plus 4 oxygens, 16 times 4. Right? So I get 136.15. 136.15 grams of CaSO4 per 1 mole of CaSO4. Right? Multiply those together. Right? Now, that's going to give me 34.7 divided by 136.15, 0.25 moles of CaSO4. Okay. Now, I have 58.3 grams I'm going to need of sodium iodide. Right? I'm just going to squeeze this in here, I guess. 58.3 grams NaI times its molar mass, 1 mole. NaI weighs, how much does it weigh? Let's find out. Alright, sodium is 20. Let's see, I'm going to multiply this. I'm just going to times it all in here. 22.99 plus iodine, 126.9. Get rid of that. Oh, I forgot something. I have to go back in here and insert, because I'm gonna divided by the molar mass has to go on the bottom here. So, all right. So that's going to be my answer. 0.39 moles NaI. Let's go ahead and get that mass down here so we can get that off of there. All right. 149.89 grams. Okay, that equals that amount. All right. Ask yourself, do I have enough NaI to use up all of the calcium sulfates? Do I have enough calcium sulfate to use up all of the NaI? Whichever one gets used up is the limiting reactant. So if I look at these moles, and I know that I have a 1:2 ratio, I'm going to need twice as much NaI as I have calcium sulfate. Well, twice 0.25 is 0.5. I don't have enough. I don't have 0.5 NaI, so the NaI is going to run out first. So my limiting reactant equals NaI. Okay, use the number of moles of the limiting reactant to calculate the number of moles of each product using coefficients. So 0.39 moles NaI times, let's see, my product here is 1 mole of CaI2 for every 2 moles NaI. Right? So 0.39 divided by 2 is 0.195 moles of CaI2. And we do this again, 0.39 moles NaI times, again, 1 to 2, 1 mole Na2SO4 for every 2 moles of Na2SO4, and that's going to give me the same number, 0.195 moles of Na2SO4. Okay? In part C, you found the moles of each product. Now convert the moles to grams using molar masses from the periodic table. Right? So I want the grams of each product produced. So I've got those here. So I'm going to put them together. 0.195 moles of CaI2 times, in this case I have moles, so 1 mole goes in the bottom, CaI2. I need its molar mass up here. So calcium is 40.08 plus iodine 126.9, but I have 2 of those in there, so I got to multiply by 2. That's going to be 293.88. Right, so that number times 0.195 is 57.3 grams of CaI2. Now let's do the same with the other one. 0.195 moles Na2SO4 times 1 mole Na2SO4 is on the bottom. I need the molar mass. Let's add that up. So Na 22.99 times 2, because I have 2 of those, plus a sulfur 32.07 plus 4 oxygens, 16 times 4, 142.05. 142.05 grams. Alright, so plug that in my calculator. So I take that mass, I multiply it by 0.195, and I get 27.7 grams of Na2SO4. Okay? That's all there is to it. Now, in this one, we're going to do it just like that, but we're going to throw all of those steps together. Okay? So we're going to do them all in just one step. Okay? First off, I need a balanced chemical equation. So I have Al NO3 3 reacting with CaO. Now, when these react, I'm going to make calcium nitrate. Calcium is a +2, nitrate is a -1. So I'm going to need 2 NO3s on that calcium. And I'm going to make some aluminum oxide. Right? Aluminum has a +3 charge, oxygen has a -2 charge. So it's going to be Al2O3. Now I got to balance it. So 1 aluminum, 2 aluminum, so I'm going to need 2 there. That's going to give me 2 times 3 is 6 nitrates. I can get 6 nitrates here by multiplying this by 3. That means I'm going to need 3 calciums here. Those 3 oxygens are right there. So I have a balanced chemical equation. All right, now I have 181.1 grams of Al NO3 3. I need to convert it to moles, right? 1 mole of Al NO3 2. Right, so let's find out how much that weighs. All right, Al is 26.98 plus, I'm going to put this in parentheses here, 14.01 plus 16 times 3. I have that times 3, because I have 3 nitrates. So if I look at my compound, I have an aluminum and 3 nitrates on it. So I have an aluminum, I have the nitrate mass added up, times 3, 213.01 grams. Okay? I want how much of each product will be produced, but I need to find the limiting reactant first. So what I'm going to do is one more step here. I'm going to convert this to this so I can identify what that is. All right, I have aluminum nitrate. All right, I'm going to convert this to 3 moles of CaO, convert it to CaO for every 2 moles Al NO3. Right, so I have those. That's going to give me the number of moles of calcium oxide that I need, that I can then compare with what I have. So let's do this math. 181.1 times 1 divided by 2, 13.01 times 3 divided by 2 equals 1.28 moles of CaO. All right, now I've got 102.1 grams of CaO. Let's find out how much that weighs. Calcium is 40.08 plus 16 from the oxygen. That's 56.08 grams. So here, 1 mole of CaO weighs 56.08 grams. All right, so this will give me the moles here. 102.1 times 1 divided by 56.08, 1.82 moles of CaO. All right, I need 1.28, I have 1.82, so I have more than enough calcium oxide. That means the aluminum nitrate is the limiting reactant. So this here is my limiting reactant. And so I'm going to use this then to find out how much of each product I'm going to make. So 181.1 grams of Al NO3 times 1 mole Al NO3 3, that should be a 3, over 213.01 grams times 3 moles of Ca NO3 over 2 moles Al NO3 times 1 mole Ca NO3 down here on the bottom, and I need its mass up here, so I have to add that up. So calcium 40.08 plus, and put this in parentheses here, 14.01 plus 16 times 3 times 2, because there's 2 nitrates on there. So this is 164.1 grams. Okay, so when I plug that all in, 181.1 times 1 divided by 213.01 times 3 divided by 2 times 164.1 divided by 1 equals 209.3 grams of this is CaNO3 produced. Spell right. Okay. Now I have one more problem to do. It's going to look almost exactly the same as this. 181.1 times 1 mole AlNO3 over 213.01 grams times, in this case, 1 mole Al2O3 for every 2 moles of AlNO3. And now I need a molar mass here, right? 1 mole Al2O3. All right, aluminum 26.98 times 2 plus 16 times 3. All right, so that is 101.96 grams. Plug that in my calculator. So I'll write that down here. All right, 181.1 times 1 divided by 213.01 times 1 divided by 2 times 101.96 divided by 1 equals 43.3 moles of Al2O3 produced. And that's how we do limiting reactant problems.